Now in today's lecture we saw how to actually find the Jordan basis, because if we just try to reproduce the proof of the theorem, you have what we call the guaranteed or Taralf method, which is really very complicated, too many variables and names and letters to keep track of. And now we learned some ways to compute a Jordan basis, how to find one. So what we used in today's lecture is again this notion of the span of a family. If we have a family of vectors which spans a certain subspace, we can make some operations on those vectors and it will not change what is the subspace that it spans. In particular, we can add multiples of some vectors on the basis to some other vectors on the basis, and this will not change the span. Another concept from Honors Linear Algebra 1 that we may use towards this searching a Jordan basis is row reduction, and how can you extend the basis to extend a linearly independent family to get a basis, or just add one more linearly independent vector to a linearly independent family. How can you do that? If you just want to add whatever vector from the canonical basis, for instance, we can write the vectors as rows. This is what we're doing on Linear Algebra 1. Then we perform row reduction, and then we get some pivots. And in the columns where we don't have pivots, we can add that vector. This works. However, this is not what we want to do sometimes. Sometimes we may have a collection of vectors, and then it's more convenient to write like this, because they are linearly independent, and besides those vectors, we want to add one more that will also be linearly independent when you add it, but you want to add from a specific collection of vectors, not from the canonical basis, let's say. And then in that case, the one thing we can do very efficient is write them as columns instead of rows, perform row reduction. What's the point of performing row reduction? Is just to identify which ones of these you can still add without making the collection linearly dependent. So once you do the row reduction, here you necessarily get pivot, 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 and if we do a complete reduction, all the rest will be 0. And from these vectors here, the ones that do have pivots will be the ones that you can add. The ones that have pivots are the ones that you can add to the collection, and so that it will still be linearly independent. It may be very convenient to do this. Now, before we can talk about how to compute a Jordan basis and understand how to compute a Jordan basis, let's briefly recall how we can define a Jordan basis. We know from this very important lecture 13, our vector space can be decomposed as direct sum of generalized eigenspaces for our operator T, and it's very convenient because T is invariant when restricted to these, so you can restrict it to these spaces, and once you restrict, it is nilpotent. If you subtract a multiple of the identity, it becomes nilpotent there. Okay, this one, it becomes nilpotent, and that's how we defined the Jordan basis. How did we do that? Well, think of the Jordan basis as a collection of threads. You have a vector, and then when you apply this nilpotent operator n lambda that I define like this for convenience, so you apply n lambda to some vector, then you get another vector, and then you can apply it again. You get another vector, you apply it again, you get another vector, you apply it again, you get another vector, until finally you get 0. When you get 0, it means the previous vector was an eigenvector, and all the ones before it were generalized eigenvectors that satisfy that equation T v j equal lambda j vj plus vj minus 1. So they are not exactly eigenvectors, they have this link to the previous vectors. And it is this collection of threads like this that will make our operator have a Jordan matrix. So when we write our operator, the matrix of this operator with respect to this basis, and this basis, it has to be written backwards. Why backwards? Because here we have vj minus 1, not plus 1, it's minus 1. That's why we have to write the basis backwards with respect to the chain of applications of the nilpotent operator. So that's a very convenient way of thinking of a Jordan basis, because that's how we can build one without feeling overwhelmed about a bunch of notations and recipes that don't make much sense. So the right way of thinking of a Jordan basis really is just a collection of threads, and here I'm highlighting that it's an eigenvector. The last vector of the thread is an eigenvector, and if all these vectors are linearly independent, all of them, then this is a basis. So we can write the matrix of the operator with respect to the basis, and since each vector in this basis, when you apply t, what you get is exactly the next one. Well, that would be lambda times the same vector plus the next one. Then this will be a Jordan form for the operator. So again, if in the end this collection of vectors is linearly independent and we have n of them, so it forms a basis for V, then this is a Jordan basis. And that's a very convenient way to think, do I have a Jordan basis or not? You look at the collection of vectors and you just see if they are ordered in threads like this, and you don't have anything like this, threads of this type. You don't have this type of thing. It's really just one vector and then it ends. They don't merge. The threads, they don't merge. Each thread eventually ends at 0. This is what a collection of threads would look like. So then from this perspective of what the Jordan basis looks like, that's how we move into lecture 16, which is how do we actually find one. So the first observation is vectors in the same thread, they are always linearly independent. That's an easy exercise. If you have a vector such that when you apply whatever operator to it, it doesn't need to be nilpotent. You get another vector, another, and eventually this thread ends at 0. It's an easy exercise. All these vectors, they are linearly independent. Another thing, which is also not so hard to show, is if these two vectors here are linearly independent, then their pre-image are linearly independent, and therefore their pre-image is also linearly independent, etc., etc. However, there is a much stronger property, and you prove that property in a similar way as you prove this condition for a single thread. So for a single thread, what did we have? We had non-zero vectors eventually end at 0. So of course we throw away 0. Then this vector here being non-zero, the entire thread is linearly independent. Well, using the same argument, is just more variables and more objects to juggle with. But using the same proof, you can actually show that if the tips of a collection of threads form a linearly independent family, then the entire collection of all vectors present in the threads are also linearly independent. So let me say it one more time. If this vector and this vector, if these two vectors are linearly independent and they are mapped to 0, and they are the very end of threads of vectors with of n lambda for the same lambda, okay, that's important, for the same lambda, then if these two, only these two, are linearly independent, then all the vectors present in these two threads, all these vectors together, they are linearly independent. And if you have more than two threads, you have a certain number of threads. So here dot 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 means you have a number of threads here in between. If these vectors here at the tip are linearly independent, then the entire family of vectors is linearly independent, which is great, because then if you have n of them, then it's a basis. Or if you have dj of them, which will be the dimension of the generalized eigenspace corresponding to lambda j, then you have a Jordan basis for the restriction of V to that space at least. And of course we'll treat one of these spaces at a time. So this property here which maybe was not emphasized enough in the lecture. It is in one of the handouts. This is a key property. It's extremely convenient. It will allow us to verify that what we found is a Jordan basis in a much more convenient way. So very briefly, what are the methods we learned? Quick and dirty method. First, quick and dirty method. It's more convenient when you have multiple eigenvalues and then you don't want to compute what are the generalized eigenspaces. So what you do is you find eigenvectors, linearly independent because you want to use this property here. So you get a basis for the eigenspace, and then you try to find pre-image of these vectors. Pre-image in what sense? Under this n lambda operator. So you try to find as many pre-images as you can, try to make these threads long. The collection you get using this method is always linearly independent because of this property here. But maybe just there will not be enough many vectors there. Now, the second quick and dirty method is a bit different, and it's more recommended in the case where there is a single eigenvalue, because then you don't need to compute what is generalized eigenspace. The generalized eigenspace will be the whole space. And in this case, you can just pick a vector at random, and you apply n to this vector, and then you apply n again and n again. What is n? N will be your operator minus the eigenvector times the eigenvalue times the identity, and you do that until you get 0. You can compute pre-images of that vector. However, if the vector was really random, typically you will not have pre-images, but it's a good idea to compute them just in case. And if you get fewer than n vectors, then your collection doesn't yet span the whole space. So you pick another vector at random. How do you pick the vector? Well, outside, of course, the span of the other vectors. And then you do the same business again. You apply n to this vector many times until you get 0, and you try to find pre-images of this vector many times until it's impossible. And you keep doing this. In the end of this process, you ask the question, does this span the space or not? If not, you add one more vector, and you keep doing. So of course, in the end, what you find will always be a spanning family of vectors. The problem is it might not be linearly independent. And so this is how this method can fail. Maybe it's not linearly independent. And this is how the previous method can fail, which is maybe it's not spanning. Anyway, these methods can be useful even when they fail, because there is a simpler method, which is a method where you're all the time operating with this collection of threads, and you're all the time asking your question, are these vectors linearly independent? Are these vectors spanning your space? And you can throw away one thread, you can incorporate another thread to your collection, you can add a vector and then compute its image until you get 0 and call that a thread and incorporate it here. You can do these operations. All that matters in the end is that the tip of these threads is linearly independent, because again we are using this property here. We're using this key property here, so we only need to check that. In particular, if there is a single thread, you don't need to check anything. A vector alone is always linearly independent because it's not the 0 vector, of course. We are looking at the vector before the 0 vector. So the simpler method is a method that allows you to recycle the work from other methods, even if there is something wrong there, even if they failed. We can use this simple method, which is based on eliminating and actually reducing threads which are linear combination of the other threads. There's one thing that is important to observe about the simpler method is when you try to reduce your collection. When do you want to reduce your collection? When you look at the vectors here at the tip, just before you get 0 in the threads, and you see that they are not linearly independent. If they're not linearly independent, it means one of them is a linear combination of the others. And what you want to do is you want to find as much as possible the smaller thread being a linear combination of the larger threads. And how do you do that? Well, you pick this first vector here, you write it as a column vector. You pick the second vector here, you write it as a column vector. And then you pick the third vector here, and you write it as a column vector. And then you do row reduction on this matrix, because then you will get a pivot here, obviously, because this vector is not 0. Then you will get maybe a pivot here, and here you will not get a pivot, you get maybe, let's say, half here and 2 here. And when you get that, what does it mean? It means the original vector, the vector that you had before you did row reduction, because row reduction applied to column vectors, it's actually an isomorphism, so it doesn't change which vectors are linear combinations of which other vectors. It doesn't change what the linear combinations are. So this half and 2 here means that the third vector equals half of the first vector plus 2 times the second vector. That's exactly how to interpret the result of row reduction that you get here. So now that you know how to express, let me bring another color. You know how to express this vector as a linear combination of this vector and this vector. How do you get rid of this vector? Well, we just add to it minus that linear combination. But how can you do this while preserving the structure of threads? Well, you go back here at this point. Now you use this vector and this vector to add here exactly minus that linear combination, means in this example minus 1/2 and minus 2. You add them here so that you get a different vector here. This vector here there has no reason to be 0, because there's no reason this vector is a linear combination of, there's no reason this vector is a linear combination of these two vectors. Okay? But you do this anyway. You add this linear combination, and now you compute this thread again. What will happen is, of course, because this is a linear operation, what you're doing is that you're adding the same linear combination to this thread. That's what the result that you will get, which means at some point in this thread you start getting zeros. Okay? When? We don't know exactly when. At latest it will be here, but maybe before you start getting zeros, which means you reduce the number of vectors in your collection, and you did it without changing the span of this family. So it's a very efficient reduction. If you keep applying it again and again and again, eventually you have a collection of vectors that still spans the same space. It just has fewer vectors. That's how you reduce a collection of threads, which is probably the most complicated step in this, but at least it's systematic. It doesn't have many variables or many instructions to keep track of. You just try to manipulate your collection of threads in a systematic approach, in a methodological way, until in the end you get a Jordan basis. And finally, let me reinforce one more time, why would you start from this method when you have multiple eigenvalues? That's because here you have to choose a random vector in the generalized eigenspace, and maybe you don't want to compute what the generalized eigenspace is. And conversely, why would this be the recommended method if you have a single eigenvalue? Because then it's very convenient to sample at random generalized eigenvectors, because the entire space is made of generalized eigenvectors, because there's a single eigenvalue, and it's much easier to just apply multiplication to a vector rather than solving equations, which is what you have to do here. Going backwards means solving equation. Going forward means matrix multiplication.